document provides an overview of how transformers excel across various fields. It emphasizes the importance of understanding reasoning in neural networks, particularly in algorithmic contexts. The focus is on examining the capabilities of transformers on graph problems, which serve as ideal models for complex reasoning processes. The image highlights the research's core areas, investigating the theoretical capabilities of transformers in realistic settings, using graph problems as a domain for testing algorithmic reasoning, and benchmarking transformers against graph neural networks. Understanding these reasoning capabilities is crucial for achieving out-of-distribution generalization, setting the stage for deeper analysis in following sections. Building on the foundational aspects of transformers' capabilities, we delve into the representational hierarchy of graph reasoning tasks, segmented by their computational difficulty. This hierarchy helps map out the types of tasks based on their complexity and the corresponding transformer requirements. The illustration highlights three main categories: retrieval, parallelizable, and search tasks. Retrieval tasks, such as determining node count or edge existence, are the simplest, efficiently handled by single-layer transformers, labeled as D1 in the chart. Parallelizable tasks, including connectivity checks and cycle detection, require transformers with logarithmic depth, symbolized by LD, for effective processing. Search tasks, like finding the shortest path or calculating the graph's diameter, demand more intricate solutions with logarithmic depth and potentially wider transformers, marked by LDW and LDP. This classification bridges theoretical complexity classes with the practical limitations and capabilities of transformers, enabling a structured approach to understanding their practical application in graph reasoning. The exploration continues with a detailed look at the theoretical scaling regimes for transformers and their alignment with task complexity. Here, we identify four key regimes: depth 1, D1, log depth, LD, log depth pause, LDP, and log depth wide, LDW. Depth 1 transformers, characterized by a single layer and small embedding dimension, are suitable for handling retrieval tasks. This is depicted in the image as they effectively solve simple tasks without pause tokens. Log depth transformers, maintaining a small embedding but increasing to logarithmic depth, handle parallelizable tasks better, as complexity grows with the need for concurrent processing. Log depth pause offers a variation with pause tokens, potentially enhancing efficiency while still targeting parallelizable tasks. Finally, log depth wide transformers, with increased embedding dimensions, address more complex search tasks, showcasing the need for wider representations to manage intricate search operations effectively. This classification helps in understanding how different architectural choices in transformers align with task requirements. The empirical validation using the GraphQA benchmark provides a comparative analysis of transformers and GNNs. Here, transformers demonstrate a strong advantage in global reasoning tasks, outperforming GNNs, particularly when more training samples are available. The left table illustrates how different models, including GCN, MPNN, and GN, perform on connectivity classification tasks with varying data sizes. The 11B fine-tuned transformer achieves impressive accuracy, indicating near-optimal performance. In contrast, GNNs exhibit superior performance on localized tasks, highlighting their beneficial inductive bias toward local structures. The right graph further supports this, showing how a 60-mem transformer improves in accuracy as the number of training samples increases, with a clear distinction between training and testing accuracy. This comparison underscores transformers' capacity to tackle complex graph tasks and their scaling efficiency when fine-tuned for specific challenges. The discussion now shifts to comparing transformers and graph neural networks, GNNs, in terms of global versus local reasoning capabilities. Transformers are highlighted for their strengths in global reasoning tasks, allowing them to collect and process information from disparate nodes effectively. This is particularly useful in tasks involving connectivity and shortest path calculations. On the other hand, GNNs are recognized for excelling in local tasks with low sample regimes. Their design, which simplifies learning local graph patterns, gives them an advantage in these scenarios. This is attributed to their locality constraints, similar to those in convolutional neural networks, CNNs, which enable efficient learning of local features in graphs. However, transformers face challenges with increased complexity when handling low data tasks due to their inherent design to attend globally, which demands more data for effective learning. The table presented clarifies the performance of various models on shortest path tasks with different training sample sizes. GCN, MPNN, and GIN models exhibit varying degrees of effectiveness, with the 60M transformer showing superior performance as the data size increases. This comparative insight further underscores the strengths and limitations of transformers and GNNs in their respective domains. Shifting focus to the comparison between trained transformers and large language model, LLM, prompt tuning for graph reasoning tasks, the advantages of task-specific transformers become clear. These models consistently outperform LLMs when tuned for specific tasks. The table illustrates the accuracy across various graph reasoning tasks, such as node count, connectivity, and shortest path. We see highly competitive results from 60M and 11B fine-tuned transformers, especially notable in their perfect scores for simpler retrieval tasks like node and edge count. This performance gap reveals that, while LLMs possess immense reasoning capabilities, their effectiveness in graph-specific reasoning remains limited without explicit training. The trained transformers, edge in tasks like connectivity and cycle check, underscores the benefit of direct training on graph core tasks, thus enhancing logical reasoning performance. More explicit training can bridge these gaps, unlocking the true potential of large models for specialized challenges. This document has thoroughly evaluated the graph reasoning capabilities of transformers, demonstrating that they often match or surpass specialized graph models. The tasks are represented in a sample-efficient manner, and the representational hierarchy effectively separates them into equivalence classes. The image visually organizes the key findings, highlighting strong performance, efficient learning, and the application of a representational hierarchy to clarify task classes. It also points towards future research directions, notably extending complexity classes and exploring theoretical implications to enhance transformer capabilities. This synthesis encapsulates the technical advancements and potential applications explored throughout the document.